assistant professor from School of Computer Science and Engineering. It's been a pleasure to have supervised Mengyang on her FYP project.
Hello, my name is Mengyang, the main developer of the CodeVQL project. If you are a software developer, have you ever faced this kind of question? This is Calvin. A software developer is about to comprehend this given software, which has a set of historical versions hosted on a website, such as GitHub. Calvin might have example questions like, what are the new colors to a specific method introduced in certain versions? How is the color code graph in the software changed from version to versions? These questions are difficult to answer. Some of them might be manually searched from version to version, but it is error-prone. Some of them are not possible to find out the answer without a high-level comprehension about the software. These are the typical questions in traditional static program analysis field. It is commonly used to identify code smell, comprehend programs, find bugs, and perform security patch analysis. But there's no existing tool that can answer Calvin's questions because they are cross-version. Cross-version analysis itself can be separated as the software history analysis. Now, we creatively combine these two types of analysis together. We come out with CodeVQL, a query analysis language that is able to perform cross-version static program analysis. Now, let's see how Calvin's question can be addressed by CodeVQL. CodeVQL provides a web interface that looks like this. It has four main components. Firstly, an input area that accepts a GitHub repository link. Secondly, a drop-down list where a list of sample GitHub repository links are available. Thirdly, a code editor to input the CodeVQL query. Fourthly, a run button to trigger the analysis with GitHub repository specified and CodeVQL query written. We input an example GitHub repository link and input the following queries. This query means to find any color that appears in the selected version v2 but did not appear in the selected version v1, and the color invokes the specified method circle.getArea, whereas v1 is specified by a unique software version identifier generated by Git, and the same as v2. The CodeVQL grammar is completely designed by me. The design of the language specification is inspired by the structured querying language, so that it is familiar to most developers. For example, keywords like from, select, and where. In addition to SQL, we define new sets of grammars. For example, the object-oriented way of perceiving the facts, the statement for defining version variables, the range statement for setting a variable on a specific version, and the reasoning statement. Now, let's see what happens inside the Run button. The following pipeline is designed and implemented by me. The selected GitHub repository and the CodeVQL query is firstly transferred to the server, and the server invokes the CodeVQL command line interface with the given input, which automates the CodeVQL internal execution. Firstly, the input CodeVQL query is translated into programs in Souffle, which is a logical programming language that the analysis engine can understand. There is a main Souffle program that contains the major part of the CodeVQL logics, and it looks like this. It declares the CodeVQL variable into corresponding Souffle variables, defines the output structure according to the select statement, and translates the conditions to rules for computing the output. There are some other Souffle programs for computing the versions that each version variable refers to. Secondly, the program fact extractor computes the program facts for the GitHub repository on selected versions. The result of the program fact extractor contains a list of files describing different types of program facts for each version. We then combine the fact files from each version. An example of combined fact file looks like this. This file describes the caller-callee relationship in the repository. In each row, the method in the second column is invoked by the method in the first column, at version specified in the third column. Thirdly, the history fact extractor encodes the Git graph into tuple attribute format. The result is a single file that looks like this. The first row means that the software at the version specified by the identifier at the second column is the software's first parent of the software at version specified by the identifier at the second column. After that, the results produced by these three components are parsed into the Souffle backend engine for analyzing, and the Souffle engine produces the eventual result. CodeVQL will be open sourced and deployed as an online service. Eventually, we want to integrate this into a software hosting platform such as GitHub. CodeVQL impacts how the software developers interact with, learn from, and build upon software histories for better and more secure software applications. It also inspires more source code analysis tools to broaden their views at cross-version analysis with the idea that the software is not developed at once.